Assalamualaikum warahmatullahi wabarakatuh and selamat sejahtera everyone. My name is Raid Zafarani Bayudi bin Rahmat, and here I will be presenting my final year project titled Programming Quantum Computing Using Python, supervised by Dr. Noor Aziza Yusuf and Prof. Hassan Abu Qasim. The goal of this project is to use the Python programming language in order to produce a simple program that can be run on a quantum computer. So first, what are quantum computers? Well, basically they are machines that exploit the weird quantum properties of objects to perform computations, instead of the classical bits that our typical computer uses today, which can only be in a definite state of zeros or ones. Quantum computers use quantum bits, which can be in a state of zeros, ones, or some superposition of both. While classical computers manipulate their bits with logic gates, quantum computers do the same thing with quantum gates. Note that, however, quantum computers are inherently probabilistic, so when the qubits are measured, they won't necessarily show the correct output 100% of the time. Therefore, many measurements are usually done by repeating the computation in order to get an idea of the probability distribution of the answer, where the correct answer should have the highest probability. In this project, we used Python's Qiskit library as well as IBM's online platform called IBM Q Experience to program and define a series of qubits and quantum gates which builds a quantum circuit. This code is then sent over IBM servers to be run on one of their prototype quantum computers, and the results of the computation are then sent back for us to analyze. The program that we made for this project is one that showcases Grover's algorithm, or Grover's search algorithm, discovered by Love Kumar Grover in 1996. This algorithm is commonly described as a database search algorithm, as it can be compared to the classical unsorted database search algorithm. It is also well known for its potential to be faster than its classical counterpart, requiring big O square root n operations instead of just big O n. However, it is more accurate to describe Grover's algorithm as an amplification algorithm, where it chooses an answer, which is the state we want the qubits to be in when we measure it. It chooses that specific state and then amplifies the probability of it being measured. This allows it to be used for much more general purposes. For example, the Grover oracle operator, UW, could pick a state representing the answer to some optimization problem, and then the Grover diffusion operator, US, would amplify that state's probability amplitude by some amount. After iterating this process a few times, the answer state will have an extremely high probability of being measured correctly. So here we have some snippets of the code that was made to create this Grover algorithm circuit, to run it on the IBM Q16 Melbourne prototype quantum computer, and then to analyze the results of the computation by drawing histograms. So here we show the results of that program we showed before. The blue histogram shows what the ideal result should look like if the quantum computer was perfect and showed no errors. The actual results are shown in the pink histogram, and as you can see, it does not resemble the expected results at all. This is due to the current limitations of current quantum computer technology. The quantum circuit we made was too long and complex, which means that the chances of decoherence errors or noise corrupting the qubits increased due to how many gates there were and how long the circuit took to complete. This is one of the fundamental issues of actual physical quantum computers, since it is almost impossible to completely prevent environmental interference and other factors. A possible solution to this is to employ error correction code to help mitigate the effects of noise, but these methods also require many more extra qubits to work, as well as an added layer of complexity to the circuit. To show an example of IBM's quantum computers working within their capabilities, here are the results for a quantum circuit that creates a Bell state in its qubits. As you can see, the circuit is very simple and short, and the results on the IBM Q machine are accurate to the expected results. Therefore, these results demonstrate the level of quantum computing technology we have today, at least for IBM's prototypes that they allowed us to use on IBM Q Experience. Clearly, we are still a long way away from seeing the day where quantum computers are in widespread commercial use, but I hope this project will motivate more students to learn about this field and perhaps even contribute to it in the future, so that we may see that day come sooner. And that is all from me. Thank you for listening.